Hello everyone, welcome back to the mechanical vibrations tutorial. Today we continue on the vibration of 2 degree of freedom systems. So as I mentioned before, this is a very extended topic and we have to spend a lot of time on that. So what we're gonna do today, we continue on the example that we had in the previous session and we explore more on how to find the mode shapes and the response of the system. So let's begin. So as you may remember, this is the example that we had before. I don't want to go into the details that what we did before because you can simply find that in the previous video. As you may remember, we found the equation of motion in a matrix shape of m1, 0, 0, m2, and then times the accelerations x double dot 1, x double dot 2 plus the stiffness matrix, as you remember, K1 plus K2 minus K2 minus K2 and K2 times X1 and X2, and then we set it equal to 0, right? And because it's a free vibration, it's equal to 0. And then, so I'm sure you can find this matrix based on the equation of motion that we had before. It's pretty simple. You remember we explained that we can take x1 as x1 cos omega t plus phi, and that's why we expect that our system behaves harmonically, right? And x2 equal to x2 cos omega t plus phi. For now, omega and phi are like general parameters, but in the future we find them specifically, especially omega. You will see that we have 2 natural frequencies and 2 mode shapes, and both system vibrates with first mode and second mode. So the total response is the combination of first mode and second mode for each mass or each component. So for now, I told you we could simply use these 2 equations, take the second derivatives and plug into above equations, basically in here. So what we end up is a matrix that basically we end up to a matrix that we should set the determinant equal to 0. So the matrix that we end up after taking the derivative and setting it up is something like that: K1 plus K2 minus M1 omega squared and minus K2 and minus K2 and K2 minus m2 omega squared times basically x1 and x2 equal to 0. And x1 and x2 here, these are capital X1 and x2 which indicate the amplitude of vibration. It's not dependent to time at this moment, right? So to find omega, or to have a non-trivial solution for this equation, we have to set the determinant of this matrix, so the determinant equal to 0, so that we can find omega 1 and omega 2, right? I'm sure that you could simply recover that from the previous tutorial. So what we did, we basically found the determinant, set it equal to 0, and basically we had omega. This is the equation we ended up, or in differential equations it's known as the characteristics equation. If you don't remember that, you can simply review our videos on differential equations. So anyway, so what we ended up is omega 4 to the power of 4 times K1 plus K2 divided by M1 plus K2 divided by M2 times omega squared plus K1, K2 and M1, M2. And then we introduced like a new variable like u equal to omega squared to convert this equation into a sort of quadratic equation, and we can find the roots of that based on the delta formula. So this can simply give us omega 1 squared and omega 2 squared, and therefore from that we can find omega 1 and omega 2, right? So basically, as you may remember, again, we could simply find omega 1 and omega 2 for this system, and we can simply find the relationships. And again, just as a sort of review from the previous lecture, for this example we have some definitions for K1, K2, M1 and M2, and which in fact give, as you may remember, we had M1 equal to M and M2 equal to 2M, K1 equal to K, and K2 equal to 2K. So this also simplifies our frequencies, and we found basically omega 1 squared and omega 2 squared equal to 2 minus plus square root of 3 Km. And why minus? Minus indicates basically to omega 1 squared and plus omega 2. As you remember, we ordered them in a way that basically the smallest one is omega 1, and from that we can find the two natural frequencies. So we have two natural frequencies, two omegas or two natural frequencies, right? And therefore we have two mode shapes, and these are again from the concepts of differential equations. These natural frequency squares are basically the eigenvalues of the matrix that we found, and the mode shapes indicate the eigenvectors basically, or modal vectors. So if you are not familiar with eigenvalues and eigenvectors, you could find more information on the linear algebra or differential equation courses, so just keep that in mind. So we have two natural frequencies, so we have two mode shapes, and remember the system or the response of each mass in the system is the combination of two mode shapes. So when we say two mode shapes, don't get it wrong that the first mass vibrates with the first mode and the second mass vibrates with the second mode. No, the vibration of each mass is the combination of first mode and second mode, and you will see in the future how we can basically combine that. Okay, so basically with the information that I just mentioned, so we have omega 1, right, which gives us or from omega 1 we can find mode 1, and from omega 2 we have mode 2. So from now on, whatever I present is new, so we'll see how we can find like mode 1 and mode 2. So mode 1 gives us the amplitude of x1 1 and x2 1. So the superscript indicates the mode shape. So as you see, it's 1, right, which means that for mode 1 the first mass has an amplitude of x11 and the second mass has the amplitude of x21, right? And for the mode 2, same thing, we have x12 and x22. So in fact it's similar to the first mode. We have superscript of 2 which belongs to mode 2. So in a vectoral representation, we have basically normal modes vectors or modal vectors. We call modal basically vectors, which for the first mode shape, so for mode 1 we have basically x1 equal to x11 and x21, right? So these are all amplitudes. So remember, capital X indicates the amplitude, which means that the mode shape is x11, for example, cos omega 1 t plus phi 1, right, for the first mode, right? So these are the amplitudes, right? So remember, these are amplitudes, right? They are not like the response. The response also has a cos omega 1 t or omega 2 t plus phi 1 or 2, right? For mode 2 we have x2, the second modal vector, as x1 2 and x2 2. So remember, and as I mentioned before, the response of each mass includes both the first mode and the second mode. So we have x11 here and x12 for the first mass, and we have x21 and x22 for the second mass. So don't get these superscripts as related to the mass 1 and mass 2. These are like mode 1 and mode 2, right? So what happens is our final response of the system for the first mass, which is written as x1t, and I'm using little x, is the combination of the two modes, which has x1 1 cos omega 1 t plus phi 1 plus x1 2 cos omega 2 t plus phi, basically I think it's gonna be phi 2. So basically it's the combination of the two basically modes, or yeah, so it's gonna be x2 here. And for the second mass we have x2t equal to x2 1 cos omega 1 t plus phi 1 plus x2 2 cos omega 2 t plus phi 2. So let's review that again. We have x11 omega 1 and phi 1, x12 omega 2 and phi 2, and that's why you see the combination of two modes appears both in the amplitude and the frequency. So for the second mass we have x21 omega 1 and phi 1 and plus x22 omega 2 and phi 2, right? So the system basically vibrates with like each mass of the system vibrates with the combination of the first mode and the second mode. And I'm repeating that because it's a bit confusing, and many students think that first mode goes to the first mass and second mode goes to the second mass, which is not true, right? So that's just a combination of two modes. For the simplicity purposes and for basically for calculation, there is a ratio which is called amplitude ratio, and it simplifies our system, and you will see how. So basically we define R I, or let's say R1, as the amplitude ratio for mode shape 1, which is equal to x21 divided by x11. Why we are doing that, you see in the calculation, we get rid of one of the variables, especially for x2 or for mass 2, and then we calculate everything based on x1 and R1, which simplifies our calculation. And we also define R2 as x2 2 divided by x1 2. So remember, this like 2 belongs to this mode shapes, right? And this 1 belongs to the mode shapes. So these are the amplitude ratios, right? Remember, this ratio are I, and I is basically R would be 1 and 2. So I'm doing that again. So I here is 1 and 2, right? So what happens is, with this definition, we have x21 equal to R1 x11 and x22 is equal to R2 x12. And why I'm doing this, we can simply go back to our original matrix representation, or we can come, what we had here was, you remember, for our system we had k1 plus k2 minus m1 omega squared, and then we have minus k2 and k2 minus m2 omega squared times x1, or sorry, it's gonna be capital X here, which are the amplitudes, right? So we have x1 and x2 equal to 0. So what I'm going to do now is to basically use this matrix or expand this matrix for each mode shape. So what I'm gonna do here is use omega 1 x11, and this is x11 and x21 here, and then repeat it for, you know, for the second mode shape, which is omega 2 x21 and x21 and x22. So let's do it. And we just, what we do, we basically have like a matrix multiplication, 2 by 2 matrix times a 2 by 1. So you can simply expand it. So let's see what happens. So if we do that, we have basically here, we have what we can do, we can further simplify it for k1 plus k2. It's up to you. So basically what we have is k1 plus k2 minus m1 omega 1. As I said, I'm going to use the first mode times x11, right? And what we had before, the last is k2, right? x21 equal to 0. And then we basically expand that matrix multiplication, and we have k2 or minus k2 x1 1 plus k2 or minus m2 omega 2, or actually it's omega 1. So we are using the first mode shape. So omega 1 squared times x2 1 equal to 0, right? This is all for the first mode shape, for like superscript 1 and for omega 1. Remember that, right? So omega 1 x1 1 here, right? So if we do this and then substitute the amplitude, like the ratios, like instead of x21 we use r x11, right? Or r1 x11. So instead of x21 we can use r1 x11. This is what we defined before. So what happens is, and now I want to use the relationship for k's and m. What we have is 3k minus, just for the sake of simplicity, minus m omega 1 squared x11 minus 2k r1 x11 equal to 0. And why I'm doing this, I want to find r, right? I want to find r1. You can imagine that, right? And the second equation gives us minus k2 x11, right? Plus k2 is 2k minus, and m2 is 2m omega 1 squared times x21. Basically x21 is r1 x1 1 equal to 0. So from these two equations we can simply find r1, right? You see, we can simply cancel out these x11s from the two sides of the equation and find r1, like the relationship for r1, which is basically we can have two equations, right? So if we look at this, let's see what is r1 and r2. Okay, so if we do this, then we get r1 equal to any of the two equations I showed before. You can use it, right? Is 2k divided by, you know, minus 2 m omega 1 squared plus k, or 2k, or we can simplify basically the 2, or like I said, you can use the other equation that we had, right? And if I go back, for example, let me just go back here. So I use this one to find, let me go back. I use this equation basically to find r1. You see, I could also use this one, right? Both of the equations may give me, you know, the same relationship for r1, right? So this is basically how we can simply find the two, variables. So this one, if we use, I actually, for the equation I just showed, I use this one. If I use the top equation from here, R1 is equal to 3k minus m omega 1 squared divided by 2k. This one gives me R1 equal to 2k divided by 2k minus 2m omega 1. Doesn't matter, both equations will be equal at the end of the day, right? So this is one, and we could repeat that for R2. So in fact, for R2 we can basically use the whole equation when we have the second mode shape. So why don't we just do that? We can simply go back to our equation of motion, and instead of like in here we can, like in the top equations, we can, instead of using the second mode, instead of the first mode, we can use the second mode. So let's do that and see what happens. So what we have here is, what we're going to do is now to find the R2 relationship. So we have k1 plus k2 minus m1 omega 2 squared times x1 2. Now we are using the second mode shape, minus k2, and instead of x2 instead of x2 2, we are gonna use r2 x1 2 equal to 0. And what we have here is minus k2 times x1 2 plus k2, this is k2 minus m2 omega squared x2, instead of x2 we can simply use r2 x2, right? r2 x1 2 equal to 0. So this is equal to x 2 1 divided by x 1 1. And from these two equations we can simply find R2 equal to x2 2 divided by x1 2 equal to, we can use either of these equations. For example, if I use the bottom one, like if I use, say for example, this equation, we get as 2k divided by 2k minus 2m omega 2 squared, or it is also equal to, if we use the top equation, we have 3k minus m omega squared divided by basically we have 2k. So as you see, the combination of them, and as you see, the comparison between this equation and this equation, they are the same almost, unlike the omega. And if we compare the last equation I just wrote here, this equation, with the one we have here basically, or we showed in here, I'm afraid you can find it here, they are very similar but with a different index, right? So we can put them in the index, like general index relationship. We can say Ri is equal to 2k, right? 2k minus 2m omega I squared, or it is also equal to what we found, like 3k minus just don't remember exactly, maybe it's m omega 2, right? So we could simply write it as m omega I squared divided by 2k, and I is equal to 1 or 2. So now we found basically our amplitude ratios, so we can further simplify what we had in our modal vectors. So modal vectors would be what, like it's gonna be basically for the first one, and if I use a new node, we have x, right, 1 equal to x11 and r1 x, 1 1 because it's x2. And for the second mode shape, we have x2 equal to x1 2 and r2 x1 2, right? So now we converted everything as a function of x1 like amplitudes, right? x11 and x12, and instead we are having r1 and r2. And how we find r1 and r2? We could simply find it in here, and as you see, it's the function of the system variables like k, m, and omega, and omega 1 and omega 2 we found them before, right? So everything is converted as a basically known variables, and we know omega. So if we plug in we know omega 1 and omega 2 before, we found them, so we can simply plug in those values for r. So if we do this, and for example, if we do it for r1 for this specific system would be 1 square root of 3 minus 1. See, it's just a number because it's a ratio. And for r2 it's gonna be minus 1 divided by 1 plus square root of 3, right? So as you see here, even we could find the magnitude of r1 and r2 because we know omega 1 and omega 2, and then we plugged it in, and omega 1 and omega 2 is a function of k and m, so we could simply find it for the system. So why don't we do that? Like let's repeat it for example for r1. So we find r1 equal to 2k divided by 2k minus 2m omega 1 squared, and omega 1 squared was equal to, I'm sure you remember, 2 minus 3 km, right? 2 minus square root of 3 km. So we plug it in this equation, and then we can find r1 as 1 square root of 3 minus 1, and this is basically a positive number. And for r2 we repeat it, we find minus 1 divided by 1 plus square root of 3, right? Because omega 2 is, you remember, 2 plus square root of 3 km, right? So this is a negative number, and I'll tell you why it is important to know which one is positive and which one is negative. So with these remarks, what we end up is like our final solution, and I don't want to go through the details. So what we found that is we had two mode shapes, and we found the amplitudes on the two mode shapes. So basically we got basically x, and if I write it here, we find x1 as like say for example a number like 1 and r1 times x11, and these are like x11 is a constant number, and x2 1 equal to 1 r2 x1 2, right? So as you remember, r1 and r2, like we know one of them is positive and the other one is negative, right? So before we basically discuss more on this problem, why it is very important to know these numbers and the directions. So it means that when the system vibrates in the first mode, or when we consider the system vibration on the first mode, and we have a positive number here and a positive number in here as well, so both masses move in the same direction like this. While when the system vibrates in mode 2, so this is for mode 1, for while the system is vibrating on the second mode, the masses motion are in the opposite direction. For example, if this goes down, the other one goes up, and it appears in this negative sign here. So this is a positive number, but R2 we know that is a negative number, right? Because we have -1 divided by a positive number. So the direction of motion of the two systems under second mode shape is opposite. Or for example, if it goes that way, this one goes the other way. However, we know that the total response of the system is the summation of these two. So that's why the system may, have different behaviors and the combination of the two mode shapes, right? So I don't want to continue more on this system because again, it's going to be very complicated. So far, we were able to find the natural frequencies of the system, omega 1 and omega 2, and we found the mode shapes here, right? This is the first mode shape and this is the second mode shape. And we knew that the final response of the system, as represented in here, instead of x2, 1 here, we can write R1, x11, and instead of x22, we can write R2, x12. So everything is a function of x11 and x12, phi1 phi2. So we have two equations like the response of the system with four unknowns: phi1, phi2, x11 and x12, because we already know R1 and R2. And in the next tutorial, I'll show you how you could simply find these four unknowns, right? So I hope you enjoyed this video. I know it's a bit more complicated when we deal with 2 degree of freedom systems, but we are going forward step by step, and I'll show you how to derive the final response of the system and based on initial conditions. So thank you very much, and please stay tuned for the next videos.